First of all, it's great to be back here, but that statement is going to get old pretty soon because I've been here quite a few times for this meeting, and it's definitely enjoyable. No snow, not freezing cold, windy. Keep it up. This is good. I like it. I'm not going to talk about IPv6. I'm not going to talk about internet exchanges. I'm not going to talk about jumbo frames. I'm not going to talk about anything that I usually talk about. I'm going to talk about something completely different. I'm talk about DNS. And in reality, I'm talking and channeling a lot of work that's being done at CloudFlare by other people, Olafur, Filippo, etc., a whole team. So in certain cases, I'll defer what I have to say, and in other cases, I'll have pertinent words. Okay, so very interestingly, I'm about to say something radically different than what was said earlier today about DNS. We actually run millions of zones in an Anycast environment that are not TLD, that are explicitly the zones run by end users. Millions and millions of small zones, collections of enterprise, high-end usage zones, a whole mixture. And they're run in an Anycasted environment. Now, what's interesting about this is that as we go through this, I'm going to talk about a few different things. What we had to do for DNSSEC to work at this scale, and what we've done for various other things protocol-wise. And you'll realize with a lot of this, we've just simply said, okay, we have to get out there and we have to be very definitive, very, very strong-willed about how we operate, because we're operating at this scale. We find things that are quite different than where we were before. So the first thing to do is just to give you a quick review of what we do. We're doing end-user DNS via a user interface, via a web interface, where people are editing zone records on a manual basis. For partners, hosting companies, we're doing large-scale API edits. A user comes along to a hosting provider and says, I want a new zone, a new domain. They may register it right there. They may move a domain. And then the back-end API brings that onto our system and adds, of course, our services, which I'm not talking about here, our DDoS mitigation, our CDN services. I'm just talking about this small DNS component that sits behind it. But that API obviously operates lots of other things. And then we end up with this last service, which I'm not really going to go deep into, but we have the service for secondarying, which is our VDNS service. But it really is quite a radically different service. And I'm going to stick to just talking about the core stuff. That just becomes something added to all of this. So we got this scale problem when we talked and thought about doing DNSSEC. This isn't just DNSSEC for a single zone. This is a DNSSEC en masse for millions and millions of zones. And not only that, and you'll see later, run where we have multiple registrars, and in fact registries, different areas as well. So we aren't even in control of a large amount of this. We are just merely the network, the DNS operator in this case. So we have to solve a few problems that are radically different than other people. But also, the speed issue became something that we started to look into rather heavily, and you'll see what we've done in that space as well. So we needed to understand just what needed to change. We needed to realize that the way you think about editing a zone file, if you we've already bashed bind once today, so I'll continue to do it. It's an easy target, unfortunately. But we don't edit zone files. We don't have that. We have this massive distributed database that goes out to all of our sites. When something gets updated with us, it gets moved out. So we actually have to rethink the way we do this. And a lot of the signing stuff that we've done, a lot of the stuff that we've done has to be rethought in a different way. Now, The good news is, a lot of this stuff we've documented, either on our blogs or via GitHub. A lot of what I'm going to talk about is actually out there in some form or other. But it definitely changes the way that you think about operating. So let's talk about scale. I mentioned earlier, but instead of it being a single TLD zone that you're looking at signing, we're talking about millions upon millions of zones, some of which change very rarely, some of which are actually quite dynamic. There's that usual sort of curve, long tail curve of usage within our system. There's nothing surprising about that. The number of data centers is growing, and growing and growing. We also have got, because of the DDoS side of the business, we've got some very dynamic records. So let's take a step back and talk about that. This isn't just end users wanting to update information. If you move your website and you use our content delivery network, you actually don't define the A record or the quad A record of the website. We do that. Because depending upon where you're viewing from or what's going on, we will change the address on our infrastructure. When we deal with DDoS attacks, we also move around A records and quad A records. So this whole dynamicism that exists within any zone, and once you add DNSSEC, all of a sudden pre-computed ideas go out the window, and you have to start looking at computing on the edge, signing on the edge, signing on the fly as needed. And also, of course, and a lot of people have, this has been a long topic of discussion, we're looking at zone protection. We just don't want people to arbitrarily list out the contents of a zone. No one does. So, this is the live signing problem. If you're doing this on batch, then you have a different problem. But when you're in the live signing, speed becomes number one in every shape, manner, or form. Because what we do on a node in Stockholm could also be done on a node in London or Hong Kong or Dubai. In other words, the live signing is done at the edge and obviously is going to get replicated on an as-needed basis. If a query comes in here versus the Middle East versus Africa versus wherever. So you're aware that you're going to do a lot more computation, but you mustn't do too much computation that it actually becomes inefficient to do that. Negative answers, we'll talk about that later. That one's sort of a fun one, sort of a secondary problem in the DNSSEC world, but when you're actually trying to do this in this environment, it becomes an issue. And then there's this, it's not artificial, but there's this real constraint on size. We have, DNSSEC definitely triggered the whole UDP versus TCP for DNS query issue. And there are ways that you can help this at the end user side. So we're going to talk about what we did in that space as well. So let's talk about what we did. Talk about speed first. We run our own in-house DNS environment. We are, let's go back to the previous talk because it brilliantly explained this. There is a massive difference between the code base you need for authoritative versus recursive lookup in the DNS world. And because we are only in the authoritative game, our code base is dramatically smaller. We've been running our own code now for quite some time. A large amount of it is available on GitHub, as I said. We are heavy users of Go programming language, and a lot of that work, again, is taken back to the community. Both to the Go, you'll see some examples of that, both to the Go community itself, but also to this completely open source available on GitHub set of libraries for doing DNS. We have to be, for that second point, absolutely resilient on attack traffic. We aren't dealing with just DDoS attacks against a particular single zone. We're looking at a whole spread. Now, we talk a lot about this, and if you're interested more about talking about DDoS, then we've written plenty on the subject, but I'm just going to talk about it, just making that statement. We've got features built into our DNS environment for other reasons, for other optimizations, our CNAME flattening to reduce the number of round-trip queries. That's all well and good until you do DNSSEC. Then you have another issue. So to be honest, a lot of this stuff is a bit self-created, but we think that that's a legitimate environment because we're solving real-world problems. All right, so ECDSA has really brought a lot to the table. I talked a little bit about this at lunchtime today with somebody, but we're talking about faster algorithm, smaller, but also the ability to to reduce the computational load. I'm going to talk a lot more about that later, or give some examples of that. What's beautiful about this is that it is a more efficient algorithm. But guess what happens in the internet world when you add a new algorithm? The question occurs, well, wait a second, am I talking to boxes out there that have got old software that won't accept algorithm 13? You know, they're built for algorithm 1, 2, you know, the usual sort of early implementations, but they weren't updated, and now we have a new set of code that we have that doesn't support it. Whether it's an early version of OpenSSL, whether it's an alternate version, or, as we've actually now found, user interfaces for doing DNSSEC enabling at registries and registrars, registrars that specifically forget to put 13 in the pull-down menu. That there really isn't, it's just a number. But because they have a pretty nice user interface, they forget to put that in there. And then on top of that, we've got this sort of ability, but because we've got small signatures, to be able to get more stuff into UDP packets than into TCP packets. And ECDSA has been discussed in a way at length inside the DNS community. We've just made, and this is one of those sort of absolute commitments, we've just made this absolute commitment to go this route, which means that all our DNSSEC signing is only ECDSA, which means that we are going to hopefully both flush out any old equipment, but take the power of the marketplace here and sort of convince people that this is the time now to finally implement this. There's a couple of URLs in there. The Go code, if you're interested in it for speed up, is work being done by Vlad with inside our London office, and this is just amazing optimization work. But let's have a look at what it looks like. And if you sign with a standard RSA, you just don't fit on a screen. This just keeps going and going and going. It's not orders managed, it's much bigger. If you sign with ECDSA, then you end up with DNS keys that literally are that big, that they're much smaller. This is, you can go into the wonderful mathematics of why this is, but enough to say that there are some great tutorials on ECDSA out there that aren't mathematics heavy and show it using very simple curves and how this works. Great exercise to go look at. But this is cool stuff. So this is some of the speed up that we did, just basic numbers. And again, this is all written in Go, all done by Vlad out of our UK office. And it gave us these type of number changes here were the things that really gave us the ability to move this code out to the edge and actually do live signing. Without this, we would have just eaten up enormous amounts of compute power. What's interesting is sort of a side note to talk about here is that it's very clear from the CPU manufacturers, go all the way down to the chip level. It's very clear to those guys, and has been for some time, that encryption algorithms, signing algorithms, absolutely need to be optimized both for power utilization and for compute time at the CPU level. And that's happened both in the mobile world and happened in the server world. So the good news is we are taking advantage of that. This is not just in a way better code, but this is code using, in this case, the Intel chipset base, and actually going deep into the instruction set where there are instructions that are very useful for doing this type of compute. So now the next issue is this negative answers. So it turns out you can implement DNSSEC fairly simply with everything I've said until you suddenly realize you have to handle negative answers. typos or whatever. And it turns out DNSSEC is quite complicated in that environment. So we had this sort of problem with the way NSEC 2 and NSEC 3 worked. We had this issue with how do we do this, because we did not want to do the heavy database lookup needed in order to understand next and previous and all of the things that are involved in a signed negative answer. And there are lots of things that in the DNS world you really would like to go back to the early 1980s and completely re-engineer, but that's just not going to happen. So you actually have to sort of go with well thought out specs, well thought out RFCs, and actually understand that you don't want to sign something 2 or 3 times on the fly in order to just get what is unfortunately quite a large number of queries. The number of queries that go in for typos, 4 W's instead of 3, for example, is non-trivial. And ignoring it has certain perils, especially in this. So we've sort of played around with this. We've written about this as well. But again, the whole goal here was to actually both get efficient NSEC answers. So although we basically are dropping back down to NSEC in cases of negative answers, this causes intermediate recursive caches not to sort of really barf badly. But it does push the spec a little bit, let's just say. All right, so there's been a bunch of work on this, but our big issue is to reduce the number of signatures, to reduce the amount of signing that we've done. And we've been able to do that while still keeping this live signing environment and not screw up intermediary resolvers in the way. So we tried this with no error. There is a couple of test servers that are out there, which actually, interestingly enough, is sort of becoming the real thing sooner than later. And you can actually sort of start playing around with the responses that we get, and the example URLs are with inside this, with inside here, and other areas. The other one was, of course, that we also wanted to reduce the amount of the size. So that's actually just an example of being able to show that we can actually get a much shorter response out of this. And the magic here is, of course, this 13 here. That's ECDSA response as opposed to an RSA response. So. Continuing with this and showing some other examples of this to sort of reiterate the point, keeping below 512 bytes, this sort of magic, unfortunate specification part of UDP versus TCP in DNS, again, reduces the amount of load on our side. So this is very much focusing on what we're doing here, and we admit that. We want our servers to be efficient. We don't want to jump to TCP just arbitrarily, et cetera, et cetera. And then let's talk about this one. So we have this other slight issue. It's built into the protocol, but we have to deal with this as well. On the fly, on a missing exchange, on a missing query, we have to generate a bitmap, and the bitmap is the bitmap of all the other answers that are there. Now, on the fly, again, self-caused problem here. So let's just talk about let's talk about what this is. We're really doing this sort of test of denial of existence. But we have, just to jump back to explain something, we actually have a rather unique environment. We own the user interface to the zone editing. And in fact, you can't put arbitrary information into our zone. You can only put in the records which we've built a user interface for. Now, this may seem very restrictive, except for millions and millions and millions of zones are on this system, and we don't get a request for some random, relatively unheard of record type. We have a very finite number of record types, and that seems to be living with the real world examples, whether it be large banks or tiny little blogs or my random ham radio website and zone, which has no redeeming value whatsoever. So what we did was we worked out this sort of minimal covering map. See, we got all of these wonderful certificates here, record types here, but in fact we don't do anything with most of them. So what we actually can do is we can simply provide a forced response here. If you ask for a text, then we can simply remove that from the bitmap and give you everything else. And it isn't incorrect. It can also be computed very quickly. It can be computed on the edge, again, part of our own requirement. But it's sort of looking at the spec and rethinking it versus the high genericism that you would have if you were doing things on a central server in a pre-computed environment. In a pre-computed environment, you'd actually know what records you have. But it actually turns out it doesn't matter to say, I'm giving you this answer for all these other records, even if they don't exist. If you were to query for them, they would generate a different bitmap. And that should be correct. So again, a lot of work in order to make this sort of edge work faster. So let's talk about key management. And let's talk about millions and millions of zones and the level of effort it takes to keep track of that many keys. That many keys could be quite complicated. So we came up with a different solution. Yes, we've got to centralize some stuff. We've got to keep certain things central. But the reality is that we can actually do some fairly nice work from that central site out to the edge. And we also can design from the beginning the ability to roll the zone signing key very quickly. Not make that a traumatic event. Actually do that on a quick, regular basis. And here's the fun part. We don't think, and this is how we're implemented, to have millions upon millions of different KSKs or obviously ZSKs, ZSKs, depending on how you want to pronounce it, within this system. So instead of looking after millions and millions of different zones with millions of keys, to heck with it, just use one. We own this whole subsystem, and we're doing this on behalf of our customers. And protecting one versus protecting millions isn't really any different. So we use a single instance of both of those, and then we can roll that out fairly quickly. So if we look at two different zones here, so this is an end user zone. And actually, you can go do this. I mean, you could go do this on a zone right now off of our servers. Here's our zone where we have our DNSSEC authoritative name servers, and these two return the identical information because they're part of the identical system, and we don't need to. We're not importing this from anywhere else. So in fact, we've significantly reduced the amount of data that we're moving around, and the getting the zone and the key signing key and working out the limited amount of communication we need out to all these zones was of great value. So this is sort of, again, part of the shortcut that we've done. So now let's talk about the external part. When you're signing something in the DNSSEC world, you've got to go talk to your parent and say, here's a DS record, and we want you to install it. And here we come to an absolute grinding halt, because we're reliant on the end user using our system to go onto their registrar and type this wonderful long string in. And this is sort of the problem. If we look at what we can do in the internet world, we've kind of screwed up the DS key part. I know full well that somebody could have taken a picture of me talking, and in the 10, 15, 20 minutes I've been yakking on, it's been posted onto Twitter or Facebook or Instagram or somewhere. It has been, I've been told. I left my phone on my desk, so it didn't beep. Okay, so internet speed. And we go down and look at all of this stuff, and when we start looking at DNS stuff, it gets pretty pathetic. If we change the registrar or we change our name servers, we sort of wait for things to time out and expire, sometimes 24 hours. And we'll see the occasional, I'm sorry, I'm moving my name servers and things are not right. When we look at DNSSEC, we really have unknown amounts of time associated with this. This is not internet speed, not even close. So let's look at HBO. And it's easy to pick on this one because it was a confluence of errors. It was a confluence of simple errors that was essentially generated by a typo. But the key point was it took over 24 hours to fix this. There was no easy fix for this. And in fact, it involved some temporary fixes in the world. This was maybe a very US-centric issue, but I'm sure that equivalents can be found around the world. But the bottom line was, yes, typo on records, got into the caches, and people were complaining that this brand new HBO service was not available. They could not get it on their particular cable provider, their particular ISP. Why couldn't they get it? Because that ISP had actually taken the steps to run a DNSSEC enabled and well-operated environment, which was going to explicitly stop stuff like this. This ability to block something because of a typo in the DNSSEC world is so simple. Go to your registrar, take your zone, and go mistype your DS record. And watch your zone just disappear off of a large percentage of the internet. If you're using 8888, Google's resolver, poof, gone. By the way, what's interesting is that this is actually sort of works a lot better now. You can type it back in correctly, wait for your registrar to upload the registry, show it up, and it'll actually show back up pretty quickly. So this whole one-day thing, I don't think really is as bad as it should be. But it's a problem. So we, CloudFlare, we have a problem. We're the third-party DNS operators. We are not a registry or registrar. And yet we have lots of information that we want to put into the parent zone. The number one thing is this DS record in order to make DNSSEC work. We also want to adjust the name server records, but let's just deal with DS for the moment. This now becomes more of a discussion, and you'll see this on the next slide, inside the domain registry world. There is no DNS operator on this sort of standard ICANN who does what diagram. Every zone, every DNS out there operates inside this diagram. Sometimes the registrar and the registry are the same player. Sometimes there aren't resellers. But the registrant, the person who actually owns the zone, that pays the money, that has the need for that particular URL or that particular zone, they're understood. They know the relationship, but there's nowhere in here where the third-party DNS operator actually exists. So there's no authoritative method for updating this. So what we want to be able to do is actually be able to adjust this. And again, this is an area that suddenly becomes more important in the DNSSEC world. Because if we want to update the DS record, going back to the end user and saying, please copy and paste this string into some other website is a recipe for disaster. And when you're at the millions and millions of zones, the chances are pretty slim that it'll get done correctly. This is work for a different community than what we have here, but it's work that we're undertaking. I just said this, sorry. It's a bad idea, cut and paste. Okay, I got a couple of minutes left. I'll skip the rest of this. It's all important, but we'll ignore it because I want to talk to you about one other thing. This. 2 minutes on a subject of any. Who here types dig commands every now and again? Who here types dig with a any query? You are not going to like this part of the presentation. You are the problem. You are the big problem. Any was a clever idea way back in the 80s, and in the DNSSEC world it's a really bad idea, but I can actually explain why it's a really bad idea today, and you can go to experiment at home to prove that any does not do what you think it does. It has problems. It can be used as an amplifier in a DDoS attack. It provides information leaks potentially in one form or another. It isn't reliable. If you think it's reliable, I'll give you the example afterwards. Come find me, talk to me. I'll give you very simple examples of why it's not reliable. But more importantly, it's expensive. It is not good for the servers. It is not good even for the intermediary resolvers. And when you add DNSSEC into it, all hell breaks loose as far as computers concerned. But the thing is that people use it at the command line, and applications use it because, whoa, this any query, it's useful. And the number one thing, and this is where I get to mention IPv6, is when people want to query for an A and a quad A, and they go, ooh, I can just do an any query because that'll return if there's an A and a quad A. Turns out it doesn't, except for people think it does. So Firefox, with inside one particular release, decided that this was part of their happy eyeball solution, and look what happens in the graph. When we query the number of any requests, all of a sudden, February this year, whoomph, up it goes. It isn't a valid way of doing this query. Find me afterwards to explain why. But we actually wrote a blog on this. And for those people following at home, we write blogs on lots of things. So, you know, that's where it is. We wrote an original draft on why this should be dropped, very short and sweet, just to get the process going. But this is what happens. When you send something out for review, the first part is people go, oh, we like that. Yes, of course. And then you get this. And of course, there is no filtering on the negative side on the internet, as one knows. But the reality is that everybody says we're going to break things. In reality, the great part was that Bernstein actually responded in person about Qmail. This was the big topic of discussion, would break Qmail. And essentially definitively stated, actually, you won't break Qmail. Qmail does an any query, but if it doesn't get anything back, we will go and do an A and a quad A or an MX record query, and everything will work quite happily. So we decided, great, Cloudflare will not break this, and there's the URL for the discussion. But why do we care about this? And it goes back to the fundamental stuff. We hate big answers. We hate things that generate lots of queries. And because we don't think it's useful in the first place, we're pretty certain that it isn't needed. But we're also willing to put our money where our mouth where our money where our mouth is, whatever the right way of saying it. So if you do this dig command, which I just did, and you dig, you know, this is a Cloudflare URL, but you could have put my ham radio call sign in there just as easily, and one of our name servers, pick the right one, you will get back this record. You will get back an hinfo record. This is a totally legal response to an any query, because any does not say all. It's anything that it feels like responding. So if you're wondering why there's no SOA or NS or A or whatever, or that nasty little text message, because this zone is, you know, using Google Mail and therefore had to validate it at some point. hinfo, and this is a much longer talk, hinfo has been thrown under the bus. It is the sacrificial zone. But the good news is we actually don't have hinfo in any of our zones because we don't provide a user interface for it. So therefore, this is totally legal. This is not taking away any information from any of our users. And please stop asking for any C draft ... Here's the draft. This is a live query as of a few days ago. And we're still in business. So play around, look at this, stop typing any. You can, you know, loop in a test if you want to. So I said all this. this actually does work. This is not a negative answer. It's a legitimate answer. But if it isn't the information people want, they'll go back. It doesn't poison anything. It doesn't cause any negative effect with inside intermediary resolvers. I'm done. I'm probably about a couple of minutes late, but if you want to read this and ask a question, feel free.
So before you ask, do you want to say if your question belongs to that category or not?
Well, actually, I have two questions. Tailing on the previous presentation about requirements for security. Signing on the fly, have you had any customers, or do you deal with customers who face regulations on how keys are handled? Like, do they have to be in HSMs? I mean, do your customers require HSM support for private keys?
Right. So the question is, what do we have from our customers? And we have a massive variance in customers. We have customers from the banking and commerce world all the way down to just random blogs, and everything in between. So the answer is yes. We do have stuff that comes from our customers, and it would be a whole other thing. About a year ago, we announced our keyless SSL environment, which is where we specifically take for SSL type queries, where we don't move the key out to the edge. And that's pretty well documented. It's been in production now for about a year and comes specifically from the banking and from the commerce requirement, where they do not want to see their SSL certificate, one example, sitting anywhere. They actually want it in their own environment, because keyless SSL enables the keys to stay inside the customer premise, not the CDN premise. Will you see the same thing for DNSSEC? At the moment, you can obviously tell no. But that is a very well understood issue on our part, and the work that we've done on the keyless side does not, for SSL, does not 100% map to this, but there are still reasons why this is a potential marketplace or a potential space for that. But stay tuned. At the moment, the answer, it says there's a single key and it's distributed to the edge. You saw that, although we can roll it very quickly.
Oh yeah, the reason why DNSSEC wasn't designed that way to start with, I don't want to get into that, but back in those days we didn't think you could do it. So that doesn't mean you're doing anything wrong, you're just doing what we didn't think was advised.
Oh no, absolutely. So, but the thing is that there is a subtle difference between DNSSEC, which is authenticating a response, versus SSL, which is securing the communication. Right. And those two are vastly different. We never built a DNS encrypted query mechanism. Yeah. And I know there's a draft to do that, but that's not part of, that's outside the scope.
Yeah. The other question I have is relating to the hinfo command or response. I'll say, have you considered trying to define a new RR type just for this? And again, not to discuss it, but I'm worried about the TXT record problem.
Okay.
Like for you, this works, right?
Yes, this works for us. I agree.
But for somebody who does use hinfo, which there might be, they might want to have a different type, and it might be good to not set the precedent. Let's talk about it later.
So we absolutely agree that we've picked a record type that is not used in our system, and therefore this is sacrificial, and it's an acceptable CloudFlare answer. But it's not a generic answer. In all of the work that we've done, we've resisted, is a better way of saying it, saying we want a new record type for ... Because that gets you into a whole different ballgame. So, there was one other question? Sorry.
Now on? Yeah. Just a comment about the elliptic curve stuff to begin with. When you say it's efficient and it's modern and it's good and it's small and it's fine, it should perhaps be pointed out that it's good for the signer. You're moving complexity from the signer to the validator. And as DNSSEC is designed, we optimize for the validator to be quick and efficient, and you're sort of offloading that. You're optimizing for your own problem space, so to speak. I'm not saying this is wrong. I'm just saying it's fair to point that out. That
Yes,
you're moving
it's
computational complexity to those guys.
I have given you very much a authoritative signer point of view, as opposed to a resolver that may or may not have to do more compute power. However, if I can balance that out, go look at some of our earlier blogs on what we've done for SSL encryption and why we've actually done some work to highly optimize the choice of algorithms in the SSL space to make mobile phones more efficient and the like. So in the big scheme of things, we've thrown out to the industry stuff to balance. But you're absolutely right. This is known to be at the moment more efficient for the signer. But as we also know, code changes over time, and so do chips. So this is absolutely going to be something that stay tuned.
I have to say that it's not a complaint. It's just an observation.
Oh, no,
I think it's a fair trade-off, especially because the original design said basically sign once, validate many times, but you sign every time, so it's fair. Another comment, as the originator of white lies, I'm happy to see the black lies, but there are a couple of small mistakes, like you don't really need the extra database lookups, etc. I do get the point with just sending back a single signature, and that's correct, and that's fine, but you wouldn't have had any database lookups with white lies either. It is a minor detail.
Worth a discussion afterwards, and we are amazingly open about what we do, and we as a company have always had a fair amount of criticism thrown back at us. Some of it is creative, so I'm more than happy to look and see whether we can actually optimize one step further. That would be fantastic. Well, we can chat later. I'd love to.
Final comment.
Yeah.
Given that you only have one key, or rather one status key, and one key signing key, how quickly can you roll?
Oh, we can roll pretty quickly. That's not a numbered answer, but we'll work on what the answer is to that. I think that I'm trying to remember what we've talked about our architecture in public and what we haven't, and I'm doing this on the fly. But I'll add that to a data point that we should add to a presentation or talk about. We're built to roll fairly quickly, and the definition of what fairly quickly is not something I've got off the top of my head.
Yeah, that's fine, but it's really interesting.
Yeah.
Because the attack surface is obviously quite large. And in spite of all inventions and tweaks to the protocol, etc., there are limits to how quickly you can roll due to caching and other parameters inside the protocol.
Absolutely. So let's talk about two things you mentioned, because they're really key. We have a very large attack surface by default because of the number of zones, but we have a very centralized is not the right word, but we have a very common attack discovery engine. So one of the things that we do on our system, whether it be for a classic DDoS attack or for a layer 7 type attack, which is really what you're talking about here, is that we actually have a common engine that can detect that and react appropriately. So this is one more layer 7 attack, but that's business as usual for us. If you look at us from a DDoS mitigation point of view, we spend an enormous amount of time working on newer and newer, and they're definitely layer 7 type attacks these days. The classic volumetric DDoS attack is actually pretty boring these days. A bunch of SYN floods, old school. A bunch of DNS or NTP queries that are echoed, it's getting old school. We're seeing a lot more layer 7 type attacks. So at least the good news is, although I'm talking about millions of zones, we actually have a fairly common environment that can detect attack traffic and react appropriately. But yeah, absolutely valid point.
Yeah. Final question. I'm a proud user of both hinfo and ANI.
I thank everybody for the time of listening to me, and over time, some of you will change your habits. Anyway, thank you very much.
Thank you.